All right, so in this lesson, let's formally learn about functions. Okay, so we are going to learn what a function is, okay, how to operate with that, and what it does for us, and many other details will come out throughout the lesson here. Okay, and so before we get started, I highly recommend that the following skills are required prior to learning about functions here. So you need to know what a variable is. You need to know what an algebraic expression is, okay, and you need to know what an equation is, and certainly you need to know how to substitute a value, a numerical value, into a variable of a given mathematical expression. Okay, and so those are the only requirements, the only sort of like the prerequisites before we head into this formal lesson here. All right, so other than that, if you're not familiar with any of those I mentioned earlier, then I recommend exit out of this. I recommend exiting out of this video lesson and view your prerequisites, okay, and before we formally head into this lesson. Otherwise, let's get started. Okay, so I'm going to need to maximize my board space here, so allow me to erase the title of the discussions here, and I'm going to also swing to the other board to bring up an example, an introductory example that promotes the idea. Okay, let's not call that an example. Let's just call it it's a problem that promotes the idea, that leads us into the idea of having a function defined. Okay, so all right, so here we go. I'm not the best artist out there, so forgive me that my hand sketch drawing is not the best, but I'm just describing the idea right here. But so a lot of times we are walking by a vending machine, Okay, so that's what it is. Yes, admittedly, I'm about to show everyone what a function is, but let's now look at a vending machine. Let's see and let's observe how a vending machine works. So all right, so now we're looking at a vending machine, and just as I said earlier, I'm not the best artist out there, so you don't need to expect that I can draw the exact picture of the vending machine, but I can draw the idea that describes how the vending machine works. So here's how it works, and I just now realized I need to make a larger diagram here. Okay, so when you're observing a vending machine, you're gonna see a price chart, and along with the products that the vending machines can give. Okay, so, and let me just create one on my own version. How's that? So how about the vending machine says you can get a soda can for $1. All right, you can get a snack. Okay, and let's say this is a very limited vending machine, so it's not going to have like different kinds of snack with just one snack. Okay, either you get it or you don't. Okay, so you're going to get a snack for at the price 75 cents. Okay, or the $.75. You can get a water bottle, okay, at the price of 50 cents. So 0.50 of $1, and you can get a coffee bottle. Okay, coffee bottle in these days are quite common out there. So coffee bottle, like a Starbucks bottle, okay, a coffee bottle. Okay, and this is for $1.25. Okay. And you feel happy, you feel satisfied with the price, or you feel not satisfied with the pricing here. That's not the point of the problem. And let's say this machine can only take exact change only. Okay, some of the quite common situation out there with those vending machines, because it doesn't have a lot of times they don't have the ability to get back the change. So I would say exact change only. All right, so here's the idea of the vending machine. We use that to buy one of these products right here. So what I see here on this, this is a product, okay? This is the product that we can get, and this is the price, okay? This is the price right there. And so how about for the price, I'm going to say the price in dollars. So the idea now is that, so how does it work? Think about it. How does it work? Okay, we walk by a vending machine and we feel thirsty. There's a water bottle. So we have to give the vending machine the money. Okay, cash, exact change only. So, you know, tentatively cash only. Okay, or maybe in these modern day, there are credit cards and all that, right? So the idea is that money, okay, in dollars, or is given it. Okay, so I'm drawing an arrow to indicate we give the money in. So is given into the machine. Okay. All right. So the idea now is we're giving it, we feed in the money, and the machine follow this rule. The machine follow this rule right here. Follows this rule, and if you give in a 50 cents, okay, if you give in a 50 cents, it's going to give you a water bottle, okay? And so it comes out with a water bottle. So I'm going to now draw an arrow coming out right here. Water bottle. Now I drew my arrow here to point at this to indicate that so we give it in, but you know, the way how machines work, we also need to make selection, but selection is not really an important part of this. But you see, the idea now is that the vending machine takes our money, okay, process that, and then as we give in the exact, so if we give in 50, that's what I'm indicating, we giving in exact change, so we give exactly 50 cents. The machine is going to know, the programmer, the programmer that designed this machine, okay, set up a rule that to tell the machine that, hey, anytime the machine sees an exact amount of being 50 cents given in, it's going to know to give you a water bottle. Okay, so water bottle comes out right here. So it's a product. Okay, and then some other time, somebody else. So allow me to use a different ink color. All right, so think about at a different time, you want a drink too, but you don't want water. You want a soda can, so you're going to input the money in here, right into that slot, okay, as dollars again. But this time you're giving it, see, I'm starting to use that term, you're giving it, but I'm using that term, you're inputting, okay, because the machine is taking it in, and we're putting it in, okay, we're putting in the money. And so the machines again sees the exact change, and the machine now recognize, hey, so now the exact change is $1. So according to the rule of this machine, and I'm starting to use that term right there, according to the rule of this machine, how it's designed, then the machine is going to pop out for you a different product, okay? I mean, it doesn't necessarily have to be different, but at least in this machine right here, it gives us a soda can. Okay, it gives us the vending machine gives us a soda can this time. All right, so the idea now, you can see primarily the idea that I would like to emphasize on is there's a rule that it takes some input value, and I'm now formally starting to use that term. The money that we're giving in right here, is referred as inputs. Okay, any amount right here is an input. You have your choice to input a $1, so you get a soda can. You have your own choice to input a 0.5 of the dollar or 50 cents to get a water bottle. And somebody else has their own choice, his or her own choice, to input a $1.25 to get a coffee bottle. But the machine will know, because the machine itself is acting as a rule. This rule determines what products to give out, to the user. And so the part that pops out right here, okay, the part that pops out right here is called the output. Okay? The output, it's a value as well. So we're inputting a value. So any of these is an input value, and any of these that comes out, it's a product, but you can also regard to that as an output value as a product. Okay, so let's keep it that way. All right, and so now I'm going to swing back, and I want to leave this here for a little while. Okay, I'm going to swing back to the other board right there. All right, and sketch another example, another problem. So, and I didn't mention any term about function or whatsoever, okay? Just hold on to that. The way I want to emphasize right now, the way I want to approach the understanding is that I want anyone learning in this video lesson to understand that what we're looking at here is a rule. The vending machine has its own rule. Okay, we don't have to know how the scientists program that machine to process, how the machine process that money to recognize that, to give you the correct product. That's not our matters, you know. But the matter here is there's a rule. The machine itself is a rule. It has a rule that whatever inputs we giving in, it gives an output correspondingly. Okay, so that's the story about a vending machine. Okay, now what about in your daily life? Now, tentatively, any of you viewing this video lesson is a student. Okay, is a student. So you must be very familiar with the following. Say the first day you're sitting in a class, especially or most commonly in a college class, then on the syllabus, your instructor, your professor must indicate the following on the syllabus. Okay, here's what it is. Okay, so let's say for something that directly relate to teachers and students. Okay, this is the kind of problem that came out very often among teachers and students. So a GPA scale, a scale that determines what overall percentage will give you a 4.0 or what overall percentage will give you a 3.0. Okay, so I have one for my own student too. The one I'm showing on the board is not necessarily the one I use for my own class, but this is a descriptive idea enough for what's going on. So, all right, so a GPA scale, let's call it that way. So right now, it's just simply a table. It's a GPA scale. So the teacher says, hey, if your final overall percentage on the syllabus of any instructor, of some instructors, okay, say if your final percentage is how about 94%, okay, or above. And I'm running a little bit out of space, so allow me to rewrite it, 94 or above. Okay, so it's not only one value here, but it's quite a few values in this interval right here. It's 94 or above, so 94 or anywhere higher than that, 94, 94.5%, depending on how precise the teacher will calculate, and then 96, 97, up to 100. Okay, so 94 or above, you will earn a final GPA. Final GPA, I'm using that term, final GPA of a 4.0. Okay, and then the teacher says if you're earning an 84%, I mean 80% or above. Now I gotta be a little bit specific about this. So 80 or above, but then 94 or above is a 4.0, and so 80 or above, it's really intense to be that's 80 or 80 or above to anywhere below 94. That's the idea right there. So you have an interval from basically this is indicating and anyone studying here, of course, you are a math student, you at least know what an interval is. Okay, and I should have also mentioned that in your prerequisites earlier. You need to know the basic enough what an interval is. So here it's an interval that anywhere from 80. So 80 is the bottom line and go to anywhere less than 94. Okay, that's another way of saying that. So 80 or above. Okay, but then when it hits 94 or above, it's a 4.0. So 80 or above is a 3.0. How's that? Okay, and then so from there on, so how about So from here, 70% or above, okay, that gives us a 2.0. Okay, the final GPA of the quarter, of the academic term, of the semester, whatsoever. And then the 60 or above is a 1.0. It's still a passing. And then anywhere, let's see, anywhere below 60. This is the way how it's commonly phrased in a lot of syllabi that I've seen out there. So this is a failing or just a 0.0. Okay, so a 0 point GPA. And so nobody wants to fall into that zone right there. But I mean, it's being a teacher, you just have to be clear. And for students, anyone being a student, you just always want to know that the very first day in an academic term, anyone as a student will ask, hey, you know, professor, what is the GPA scale? And there you go, you have one. Okay, so now, why do I bring this up in this lesson about function? Now, how is this being common with the earlier problem I brought up earlier? I brought up the vending machine. This is here's the way how I see it. It's particularly useful for teacher and students to determine final GPA for any particular individual student. Okay, because the student can also calculate on his or her own. The student can just go through all of the coursework that he has earned and find out for himself or herself that wherever he stands at in terms of the final percentage. So if the student says, so I wrote this table a little bit backward, but see, from students or teacher, if the teacher is helping the student to calculate, to figure out final GPA, then the teacher, okay, or even students can do this. Teacher or a student can just simply put in a value. So I put an arrow right here indicating, hey, the students say my final percentage is a 75. So 75 falls right into this zone right here, this interval right here. And so the rule, according to this rule, so there you go, I'm using that term again, according to that rule, I'm using that term, the rule again. The rule of this professor says if you're anywhere in this zone right here, okay, let's say the student is at 75% for the final GPA, okay, 75% for final for overall percentage, then that final percentage falls right into this particular interval, and that interval is determined will determine the final GPA to come out as a 2.0. So do you now see the similarity between this problem and the problem I brought up in the earlier example where it was a vending machine? The two things are completely different. The vending machine problem and here the GPA scale problem. But the idea now, once again, what I see here, this scale itself, here's how I see it. It's a rule. It's a rule. Okay? We're giving in a value. In this case, we're taking a percentage, a final percentage, or an overall percentage at the end of the quarter, at the end of the academic term of a student. So here's an input. Okay, so I refer to this as an input. And then this rule helps us, or this rule determines, based on the inputs, based on the given inputs, this rule determines the final GPA that any student desire to see. And then that final GPA here is regarded as the output. Okay, as the output. All right, so two examples, right? Two examples, two quick little problems. So before I move on to another one, let's have a look at this. Okay, so on the other board with the vending machine, see, I really emphasized that earlier. So what the vending machine itself, it has a rule so that it can take any inputs you give. Okay, it takes some the inputs you provide. I shouldn't say any inputs because we will get closer to that. But the idea now is that among these allowed inputs, okay, then user can put in an input amount. The machine has its own rule, so it's a rule here. The machine itself is a rule. The machine has its rule to process the inputs and come out with an output. Okay, and then so here we recognize the exact similarity there again, even though it's a completely different situation. This GPA scale here is a rule. Okay, it's a rule. The students or the teacher who would like to calculate, who would like to find out what's the final GPA of a student, can just simply input that overall percentage. Okay, and of course this overall percentage must have been calculated somewhere else based on the teacher's personal calculator or anything like that. Okay, but once you've had a final overall percentage, you can just input into the scale right here, and this scale determines a final output right here, being a GPA. So you're inputting in this case, you're inputting an overall percentage, and you're outputting the rule here, outputting a GPA. Okay, there's a rule. It takes an input, it gives an output, it determines an output. Okay, so I'm using the word it gives, making it sound like it's like a person, but yes, basically it's like a machine as well. Okay, it's taking an input and it's giving an output. It's taking an input and it's determining an output. Okay, so just like that in the other vending machine problem, and I apologize if I keep repeating, but I really want to emphasize that it's a rule. It's a rule. It takes an input, it goes through the rule, and it processes that, right? And it determines an output. It's taking an input, and according to its own rule, it's giving an output. Okay, so you start seeing you will at this point, after two situations I brought up right there, you should have started having some click in your mind. Okay, so I'm going to go to the other board. I'm going to clear out that GPA scale problem right there, and I'm gonna how about put up another problem right there. So now what about us, for the people who are specifically learning math? For math students, I'm pretty sure you have seen things like this. So let's say you have a given expression. And that's why I said earlier, the prerequisite for this lesson is simply you just need to know what an algebraic expression is all about. So now you given an expression as following. So you have an expression given is 3x minus 1. It's an expression. The reason we call it an expression now, well, hopefully I don't have to go too far back into the even further elementary algebra, but an expression, it just tells us, what this will do. Okay, so, or it indicates that any reader who reads the problem here, say, according to this expression, it says whatever the variable is. It's a variable, so it's another term among the prerequisites that you need to know. So once you know what the variable is, once you know a value of the variable, this expression tells us that we just simply multiply the value being represented by this variable with 3. So 3 multiplied with the quantity represented by the variable and subtract 1. So for now, it's simply a mathematical expression. It's an algebraic expression. Okay, 3 times the quantity represented by the variable x here, minus 1. Okay, so what you have here is an expression. And I didn't say anything about function or whatsoever. Don't worry about that. Okay, all I need you to understand is this is an expression, just like any of those expressions you have already learned prior to studying in this video lesson. Okay, so it's an expression. And so now, yes, just like that, let's make a quick note. So x is the variable. Okay, that's it. And you will also have tried this, have already knew about that, well aware about that x is the variable. So now how about, so I want to say the following, okay? Some textbooks, some instructor, I want to show as many different ways as possible. Some instructor in some textbooks say compute, or some instructor, some textbook says evaluate, okay? Or even find. Okay, compute or evaluate or find the final value. Okay, if or for if x equals 1. If x equals 1. So the idea now is that this expression is only a general expression that says, hey, anytime you know the value for x, you're just going to multiply x with 3 and minus 1. Anytime you know a value for x, then generally you just, according to this expression, then it generally tells you that for any value of x, you're going to just multiply x with 3 and minus 1. But now, since in this problem we step a little further, we're not generally looking at the expression anymore, but now we want to specifically come up with a final numerical answer when x equals 1. Okay? So when x specifically equals 1, what does this expression say? This expression says in order to calculate, to compute, to calculate, I also forgot, I should have also mentioned that term, calculate. We can calculate, we can say we can compute, or we can say evaluate. Basically we want to come up with a final numerical answer. Okay, so when x equals 1 specifically, okay, so this expression tells us, indicates for us that we multiply 3 with the quantity, now no longer represented as an x, but specifically 1. So 3 times 1 minus 1. Okay, so a lot of different ways we say we're assigning, we can say that we assign x equals 1, or we assign 1 to x. I should have said that. We assign the value 1 to x, and then now once we know that x is equal 1 right there, then this expression can proceed further to come up with a final value. So 3 times 1 minus 1. Okay, and by the way, needless to say, you need to know how to do basic order of operation. Okay, so multiplication comes first, so 3 times 1 and minus 1, we're looking at 2. Okay, so we have a given expression. We're giving our variable a value. Okay, and this for now, the variable is just simply a variable being part of it, the expression right there. We're giving our variable, we're giving in. Okay, we're giving our variable a value, and then this now all of a sudden we realize that the 3 times 1 minus 1, the 3 times the value minus 1 gives us here an output. Okay, it's an output here, but in the end, this 3 times 1 minus 1 is a rule. Just now we recognize that it's a rule. We can treat that just as a rule, just fine. Okay, so now to clarify, x equals 1 that we're giving it, that we're providing it. Yes, it's an input. It's an input. Okay, see, so right here it's an input. And this expression itself, all of a sudden we realize it has a different meaning. It has a different impact for us. We can use that as a rule. Okay, so once this is given, once this expression is given, we could try it again. To emphasize what I'm saying, that the 3x minus 1 is a rule. Okay, I chose x equals 1. We can choose x equals 0. Okay, now it's a different value assigned to x, but this rule stays the same. 3 times 0 minus 1. And that's why I can say that it's a rule, because regardless of what value we're giving it, it has to follow this. It has to follow this specific expression. Now we call that it's a rule. Okay, so 3 times 1 giving us, that's making it the 0 minus 1. The final outcome, the final output there is a negative 1. The final value is a negative 1. So again, what I see here, that's the rule. Having a little bit struggle with writing in a narrow space right here, but it's a rule. The three times the input right here, the 3 times the variable value minus 1, that's the rule. Now all of a sudden we realize, because we can apply that exact same thing on other values, and then this specific part right here is the input. Okay, because we are providing it, because it will be substituting in for the expression, and then this final outcome right here, the rule determines this. The rule determines this final outcome. So this is now, we can now call that it's the output. Okay, so same expression right here, but you come up with different values right here, depending on your beginning input right here. But in the end, what's the similarity with the two earlier examples I brought up, the two earlier situations I brought up? There's a rule. There's a rule. And we have our right to give an input. Okay, and here the input, here specifically in this mathematical expression, the input is just a value, an actual numerical value for our variable. Okay, and then the expression itself is a rule. And sometimes an expression here has another name. It's a formula. An expression can also be a formula. Okay, so according to this formula, according to this expression, now we see that as a rule. Okay, it takes this input. What does it do to the input? This rule tells us to multiply the 0 with 3. The inputs here we multiply with 3 and minus 1. That's the rule. And in this case right here, we clearly see how the rule is ran. The rule is ran by just 0, the inputs times 3 minus 1. And that's that. After that process, we come out with the negative 1 as the final output. Okay. All right. So from the vending machine problem, which is still here on my other board, from the vending machine problem, we realize I brought up to intentionally mention about there's a rule. We can input a value, and the rule will base on the value to determine the output for us. Okay. Earlier, before I erased and wrote down this expression, this algebraic expression, then the GPA scale problem was also about there was a rule, the chart itself was a rule, and then we're inputting a final overall percentage. The rule of the GPA scale, see, that could be just one rule. I have a different rule, but the other professors have a different rule. Okay, but the GPA scale itself is a rule for that, whatever class that is, and then your final overall percentage will come in through that rule and will determine a final GPA for the student. Okay, and so there's a rule, there's an input, and there's an output, and just like how it was, and this is here a lot more friendly to those who are concurrently studying math, who are specifically in math. And this problem is the closest example. It lives right in our daily lives, at least for the length of an academic term like that. Okay, so an expression now, a mathematical expression with a variable is now a rule, where you can give a different value, different values for your variable. Okay, so x here in this case is the variable, and the whole idea of variable is we can take different values. And so you know all of that idea prior to learning in this lesson, and so you can switch to different values. So according to this rule, right? So the different values that we switch to on our variable right here, we can call that, we regard to those as the input. So the variable x here is the input. Okay, we're giving it into the rule here, and this rule says that we're going to multiply the input value with 3, specifically for this rule. Multiply the input value with 3 and minus 1. Okay, and that's what the rule says, and the rules, according to that rules, and we determine that the final value here has to be a negative 1. So that final value comes out from this rule, so that's why we call it, it's an output. Okay, it's an output value. Okay, it's an output value. And so now we are ready to put all of the details together. 3 things we have spotted so far, 3 things we have seen so far. Most importantly, it's a rule. 3 different examples I brought up right there. They're all having a rule. There's a rule, and then that rule can take an input. Okay, and then the inputs and the rules processes the inputs and to determine an output. Okay, and so now let's put it all together. So throughout the 3 examples, here's what we recognize. What the 3 examples have in common. All right, so I've mentioned it, but now let's formally write it down. So what's common? Okay, and of course I mean what's common here is what's common among the 3 examples that I brought up. All right, so the number 1 thing, most important one, is a rule. Any one of those I brought up, it's a rule. Okay, it's a rule that's relating. Hey, we're taking one value, inputting, and then we determine that. So in the end, input and outputs, they are relating. They are related. That's why I'm using this term. It's a rule that's relating the two variables. Okay. Now I'm starting to step outside of the box a little bit, but so I thought I only mentioned the term variable in the very last example, but in the end, think about it. If you're looking at your own understanding of a variable in a broader understanding, then the inputting amount here, you can change to different quantity. You can change to different value. So the pricing, the money that you're giving into the machine, it's a variable. Okay, it's a variable. Yes, I understand we've learned math long enough to the point that anytime we think of variable, we think it's a numerical value. Okay, so here it is. Yes, it's numerical value. It's money. But here's the thing. Having different product, it's also a variable. Product itself is a variable. These are different values. The product can be either a soda can, or a snack, or a water bottle, or a coffee bottle, or well, this line doesn't count. So we only have 4 different values according to this table over here. But in the end, my point here is that being a variable does not necessarily mean it have to be a numerical. It's to represent a numerical quantity. It doesn't always have to be like that. Yes, we promoted the idea of variable starting out with quantity, but now just simply a variable can represent different product here. That's a variable. So we take this inputting here is a variable, and this output here is also a variable. Input is a variable, output is a variable. And that's why, back to what I said about what's common among these three, the problems I brought up, there was a rule. In any of those problems, there was a rule that's relating the two variables, the inputting variable and the outputting variable. Okay, the input variable and the output variable. And yes, see, there's an input variable, the one that we're giving in. Okay, it's called the input variable. It's given in. Okay, and then I leave a little space because I want to come back here and make some further notes on that. And then the rule process the inputs, as you already saw how that worked. The rule process the inputs to determine the output. So we come out with an output, and the output itself is a variable. Okay. See, this output variable or this output value is determined by the rule. So the rule, to me, is the most important thing. There's a rule, and then it takes an input and to determine, to calculate the output. Okay, so determine is a more the general wording of that, but calculate in case it's a numerical value, then we can calculate and get an output. All right, so, but here's the thing. Just having these three elements is not enough to make what's so-called a function. Okay, it's not enough to make what's so-called a function. So here, let me come back to the vending machine problem. Okay, because yes, you have already up to this point knowing that any of the example problems, I keep avoiding saying the word function too rushly. I want you to nail down that in any of these examples I brought up, there are 3 common things. Okay, there are 3 common things. Having a rule, it takes an input and it gives out an output based on the rule. Okay, but now there's actually one more hidden factor, hidden secrets that now need to be brought out right here. Let me go back to the vending machine problem that I brought up earlier. Okay. Now, just simply being a rule that takes an input and gives an output, sometimes if a rule is not well done, okay, and what do I mean by not well done? So here's the thing. You see, a well done rule in this case, to make users happy, right? Think about it. The rule have to make sure that any input you're giving in gives out exactly only one output. Any inputs, for any inputs giving in, the rule only gives out exactly one output. Why is that so important? Why is that so important? Okay, when I'm saying this is what I mean right here. Just think about it. It's a machine, right? It takes $1. Today, for this user, it takes $1. It gives out a soda can, and without any modification, all of a sudden tomorrow it takes for the next user, it takes $1, but it gives a snack. That means the rule has gone wrong. It could still be a rule that takes the money and giving out something, but the rule is not giving a satisfaction answer, a satisfying the output right here, because we want a rule to be set with one particular the agreement that you take an input, you only give out one exact output. So if you're running this rule again, provided the input is $1, you have to end up with a soda can. Okay, it makes no sense that, hey, going in with a $1, and according to this rule, it makes no sense that going in with $1 and then you give a soda can, and the next time you come out with a water bottle. That's a bad and an ill-designed machine. Okay, so a well-designed machine is you're taking in $1. Okay, you run it once, it's giving out a soda can. You're taking in $1 again. Okay, and the next time it gives the same soda can. That's what it means by being a one output, one unique output right here. Okay, and so just like that. Now, allow me to quickly erase this. And now I'm going to quickly bring up that GPA scale again. Okay, so for the GPA scale, final percentage, overall percentage, 94 or above. Allow me to use that up arrow over here. That's a 4.0. Okay, 80 or above, that's a 3.0. Okay, 70 or above is a 2.0. Okay, and 60 or above is a 1.0, and then anywhere below 60 is a 0.0. Okay, so we're having an input. Okay, there's inputs coming in. Now you know what input you need to give it. You need to provide this. You need to look it up by having a provided final overall percentage, and then you're going to come out with an output. Okay, being the GPA, being overall percentage. Okay, but here's a problem. So if you're giving in one value, the good scale, or a fair professor, a professor who is consistent, say if the student is earning at the end of the quarter, at the end of the academic term, 75%, then he's going to look into this chart. The professor is going to look into this chart and say, hey, your final GPA is a 2.0. Okay, but if a different students running into a 75% again, but for some reason the professors go through this chart but giving him a 4.0, that means the same 75 but coming out with two outputs, a 4.0 the next day or for different students, and then a 2.0 for the students. That is not good. At least for the job of a teacher, being inconsistent is so not good. Okay, it's so not good. So once you set up this rule, it has to be applicable to everyone, and anyone with that same number has to only come out with this. Okay, now I'm not saying that, and it's different with saying that. You see, you can still have 76% coming into the same 76 and 75%. I drew it in the wrong slot. 75% and 76% are in this slot. Now, sometimes two inputs, two different values of the input can come up into one particular output. That's completely okay, but for each of these, the way how I see on each of these, once you are given it, once you know that you're on this particular input, you only end up with one output. Okay, it makes no sense that the students with a 75%, some students with a 75%, but the teacher told him, hey, you got a 2.0, okay. But another student with the same exact input, 75%, but the professor tells that other student, you got a 4.0. So that is something not fair about the instructor. Okay, something very inconsistent about the instructor, or the rule here has something funny going on behind the scene right there. Okay, and that's the unique feature of being a function. Now we get clear to that idea right here. Okay. So one unique thing that was a little bit hidden, but now I just brought it out to light right here is that, okay, each input, okay, each input determines one and only one output. All right, each input. So any of the problems I've done earlier, and including the expression 3x minus 1 that I brought up before I erased it. You see, you're giving one input. X equals 1. 3 times 1 minus 1 equals 2. Okay, the calculations say so. If the next day for a different student is x equals 1 again as the input, but 3 times 1 minus 1 equals 5, something's not right. Okay, something's not right. So in the way it is, it needs to be only one output. So if it has multiple outputs, it's a completely different story. So what we want to focus to is each input determines only one and only one output. Okay, no exception. No exception. All right, so now in that way, now we are ready to formalize the idea here. So allow me to put down that quick list again, that list I brought up earlier about what's common among the 3 examples I brought up earlier. And at this point, I erased things all over, but I hope you retain with you. I'm talking to whoever learning in this video lesson. I hope you retain with you that I brought up 3 examples. One of them is the vending machine problem. The other one, the other problem is the GPA scale. Okay, and this just now is the mathematical expression, a very common mathematical expression. Okay, and then I'm now again gonna write down what's common, but we're gonna add on top of that. Okay, what's common about among the 3 examples? So there's a rule. Okay, there's a rule relating to variables. Okay, we knew that. I already brought it out. Okay, and then of course, so those 2 variables, one of them is called the input variable. All right, it's the inputs variable, and then yes, this value is given in. Okay, and then the rule will help determine, based on the given inputs, the rule will help determining the output variable. I mean the output value, and so we can come up with different values, right, depending on what inputs we're giving it. That's why generally the output is a variable. So I tend to call it an output variable. Okay, so it's calculated or it's determined by the rule. But now, so I wrote these 3 down earlier, but that's not all the things that need to be that are common between the 3 examples. There's one more that I just now brought it out. Okay, so each input, okay, each input, okay, determines just exactly one and only one. I'm making it extra strong about that statement. Exactly one and then and only one outputs. Okay. Each input through the rule determines exactly one and only one output. Okay. All right. So now, indeed, at the end here, we actually have 4 fundamental characteristics. The number one thing, the most primary thing, the most primary characteristic, it's a rule that's relating two variables. But then not only a rules. Now, so the two variables are the input variable and the output variables. That's easy to know and quite directly relating to this. What I said earlier, it's a rule relating two variables. But then that rule is not just relating. It's not just relating. It has to relate in a way that each input, okay, each input determines exactly one and only one output. That's what matters right there. That's how important it is to have. All right, so at this point now we are ready for a formal definition of what a function is. So allow me to swing by to the other board and erase the board and then write down the formal definition. All right, so there are now in these days so many textbooks that offer so many different way of wording the definition. So allow me to have my own way of wording the definition of a function. Okay, so the definition we're doing here is the definition of what a function is. Okay, and so a function is a function. And now it's a new terminology and it's a new language. All right, now we formally start using that term. A function. All right, is a rule. Yes, a function is a rule. First thing, be clear, a function is a rule. Okay. But now it has requirements. It's not just any rule out there. Okay, a function that is a rule that determines exactly one output. All right, for each input. And of course, each given input. All right, a function is a rule that determines exactly one output. See, so it's a rule. It takes input and it gives output. So that's why back on the list that I listed down, the common, what's common between, among the 3 examples, and yes, there's a rule. Okay, so the first thing to nail down anytime we hear the term function, hey, we have a function to work with. Okay, so this is the function and that is a function. Think of a rule. It's a rule, and that rule will be relating to variables here. One of them we call inputs, the other one we call outputs. That's what it says. A function is a rule. It is a rule. A function is a rule that determines the way that it takes the inputs and it determines the outputs. But it determines, here's the requirement. So the bottom one that I wrote on my other list, exactly one output for each given input. Okay, so that's in one statement, in one sentence. That's how we define what a function is. Okay, so now from now on, and there are many professors out there who would like to explain, and you have to understand, many professors explain the idea about a function differently, but any of them, including me, has we have our own way of interpreting what a function is, but any of them and all of us, eventually we all come to the same understanding. Okay, so that I would like to emphasize for my students, whoever learn with me, that a function is a rule. I want my students to see a function is a rule. Okay, that's the most important thing to emphasize. And then that rule has a requirement. It has to determine exactly one output for each given input. For each given input. Okay. All right. So now that for better communication, just better communication, either a written form of communication in math, then let's come up with some notation for function. Okay, so that when you write it down, it's an international way, so that when you write it down, anyone in the world will understand that, hey, what you write down there is a function. Okay, or when you read a notation, okay, doesn't matter if the written communication was from a person who is speaking a different language, but once you see the notation, you must understand it's a function. So let's look at the function notation right here. Okay, so it could be a title of a discussion on its own, but I would like to just put this as a subtopic, you know, in our main general understanding of what a function is. Okay, so it's part of our current going on video lecture here. So now we're looking at function notation. And I'm going to show you a couple of different varieties. Okay, so function notations, different ways of how we notate a function, how we can, on written form, okay, on written paper. Okay, so now let me start with that third example that I brought up, that third promoting example that I brought up. Let's look back at that rule. So now everybody agree with me that it was a rule. So 3 times x minus 1, and we investigated this clearly. This rule says anywhere we have an input value, right? Once we give an input value for x, once we substitute a value, a numerical value for x, then this rule says we multiply the input value with 3, and then minus 1. And I do my work here to follow strictly with the order of operations. And so there's a rule. Okay. And now we have investigated further that one input gave out only one output. So now clearly speaking, this is this rule clearly is a function, because this rule meets all of the requirements to be a function. It's a rule relating between an input, and it comes any inputs assigned, we come out with an output. And then any one input only gives exactly and only one output. So this rule here is a function, clearly. Okay, but now we don't want to always write this down. Hey, 3x minus 1 is a function. It's a rule and it's a function. We don't want to always write this down like that. And that's the whole purpose of coming up with a function notation. Okay, and so now let's roll back to that point where we understood already that this is a rule. The rule says from this input, right, we're gonna multiply that input with 3 and subtract 1. So with this rule right here, I'm gonna name the whole rule. All right, I'm gonna name the whole rule here as I'm gonna give a letter. And the letter choice here, yes, very traditionally, the authors throughout many textbooks use a letter F, a lowercase letter F, maybe because that's starting out for function. But it's just a name. So this whole expression here can now, in short, be represented by a name F. And this is a function. So the function here has a name, F. And now in this notation, after indicating the name of the function, now I'm going to use a pair of parentheses. And I'm indicating with the x. So now this x has to be matching with that x in our rule over here. So that's the whole notation of our function. So this 3x minus 1 is a function. We name that x. And it's a function where it's indicating, so this parentheses with this pair of parentheses with the x indicated here, it's an indication that in this expression, the x that appears in our expression, in our function, that is the input. Okay, so now with this notation, let me break it down even more in detail here. Okay, so just the f itself. Okay, just the f itself. This is our functions. It's the name of the function, or for short, it's the function's name. Okay, it's the function's name, just that letter, and then the x being, and so it's always, if you just write fx right here, right like this, it's not enough. You have to indicate the x with a pair of parentheses around. Okay, so, and this is the proper notation for that. So the x that appears inside of the parentheses, of the pair of parentheses, it's an indicator. Okay, there's an indicator. It indicates. Okay, it indicates that the variable x in the given rule. Okay, in the given rule, this rule initially came out as an expression. Okay, and so it now indicates the rule here, the x in the given rule is the input. Okay. All right. Now, I would like to also deliver this understanding. I would like to deliver, even though at this lecture right here, anyone at any math level can understand, but for students who are specifically in pre-calculus course, or at many institutions referred to as the college algebra, which is the algebra, but at the higher level, the much deeper level, right before you going into real calculus. So you must have heard about functions somewhere here and there when you have already arrived at a pre-calculus course, but we're still looking at those concepts again in case you have seen it again, but we're looking at that in a much more detail. So allow me to mention these details that's suitable for a student who is in a pre-calculus level course right here. But see, the reason we have to, the reason why it's important, because this information is not told in any course earlier than a pre-calculus course, but the reason it's extremely important to indicate what the variable is in our expression, because now once you arrive at a pre-calculus course, you have seen enough math expressions that sometimes a given expression could be like this. Let me just pick out a scratch space right here. It could be a 3x minus c and plus a b right here. 3x minus c plus b. So we used to know that a letter represents a variable. A letter represents a variable. So in something like this, well, it's a rule. It says whatever x is, but together at the same time with whatever c is, and together with b is. So in other words, we have three variables in this expression. Okay? And so here's the thing. So it's a rule. It's a rule, multiply x with 3, but then minus whatever the value for c is, and plus whatever the value for b is. We have three variables involved in one expression. Okay? Three variables involved in one expression. But see, with this rule, it's a rule. Coming out from its truest sense, it's a rule. But then, if you would like to treat, in this rule right here, if you would like your viewers to understand that x is the main input, then you write this rule as a f of x. That's why the x here is important, because out of the three available variables, out of the three available letters, they're all variables. But the primary one to be decided according to what you want your readers to understand about your function, then this indicates that among all the 3 or 4 variables here, the x is the main input variable. Anything else, it could be whatever, but in the end, they are just constant terms, okay? This can be changed depending on what input. So once an input, or in other way of saying, once an input is given, then only the input value is substituted for x, not for c, not for b, okay? So think about it. Consequently, the same rule right here, the same rule. But see, if we are focusing on c as the main function, then I cannot call that the same function f anymore. It has to be a different function. Even though the rule, the expression is the same expression, but we have to call it as a g function. But now this function g takes the inputs being the c letter. Okay, so if you're looking at c equals 1, for example, then it has to be preceded as 3 times x minus 1 plus b. Okay, and I'm a little ahead of myself in terms of showing you that how to substitute in, and we will get to all that. But see, so my point now is that that's what I'm trying to explain. I'm trying to explain the importance of why we have to indicate the input variable in a pair of parentheses. Okay, because sometimes we might end up with one expression like this where abstractly it has so many terms, so many variables as letters. And so in a problem like that, then we have to, it is strictly important that we indicate the input variable's name so that viewers, users will know that this is the main variable, the main input variable. Anything else is just either constants or coefficients. Okay, and at this point, of course, when you're learning in this video lessons, you must understand what a coefficient is. Okay, so now, so back to what I was in the middle of saying. And so now, function notation. So f in parentheses, f is this function's name, in parentheses x. So this part right here, this part of the notation, the in parentheses with the x, that's the part where it indicates which letter in here is designated as the input variable of our expression, of our function here. Okay, and so now I need to erase my red notation here, my red note here, because I need space to write. But so once we come up with a notation, then we have to learn, we need to get use of how we say it out. Okay, at least in English term, then this symbol, this notation, the way we say it, the way we read it out loud, f of x. Okay, that's the way we read it, that's the way we read out loud, that's the way we pronounce it. Okay, this notation, we read f of x, but it means it's a function with the name f. And then, so f now legally represents that rule. Okay, and then to be specific, and very important to be this specific right here, that this function takes the x as the input variable in case one function may involve to more than one letters involved in your expression, like that. Okay, and so now, and so in that way, it makes sense perfectly. It makes sense logically that and upon giving it a notation, then the whole idea now together, we have already agreed that this is a function, and we learned about the function notation. So now it logically it makes sense that we write f of x. Anytime you would like to communicate with people, with user about, hey, here you go, here's my function, to work with that. At least for me being a professor, is handing down a function to my students. Hey students, I want you to work on this problem. Then I write f of x logically equals 3x minus 1. Okay, so there you go. This is the function name. Once again, that's the logic of that function's name. This indicates when you're looking at this expression, look for that x. That's your input. Because another way of saying, another way to explain why indicating the x input variable here to be important is that once you see this, then when it gets to the step where you substitute value in, then you will know which variable to substitute value for. And then this is the rule. Okay, and so welcome aboard. This is a formal function notation. You write function name in parentheses that indicates the variable's name, and then it equals to the actual rule, where the rule is. All right, so in that problem, so why is this convenient? So now it's not a formal example yet to be brought in this current lecture, but I will bring in some formal example. But for now, let's quickly see how convenient that is. So once you call this rule right here as a function f of x, that's how I say it, but as a notation f in parentheses x. Once we give it a name, then now on my other board here, let's look at the impact of coming up with a symbol. Coming up with that notation, here's the impact. So now, see, So now when you are looking at f of 1, for example, this is how we read it. F of 1. No longer x, f of 1. But see, this is the convenience of using a notation right here. That means, this means x equals 1. We substitute 1 in place of x. We substitute 1 in place of x. And so it means now, see, x here, and compare with the original symbol, compared to the original notation f of x, then this is, instead of being x, it's 1 here. So that means in our expression, 3 times the input, 1 minus 1. Okay, and so now according to the rule says we multiply 3 with the input. So 3 times 1 minus 1. Our output here is 2. Okay. All right, so in that way, so now we are starting to get a little better, getting a little through, okay, with the function notation, and see how convenient that is. And so now allow me to, I'm still leaving this particular one on the board. So what about f, okay, of 4, and you can see it, I'm saying it out loud in front of the camera right now. F of 4, see, saying it, f of 4. But so wait a minute, compare with the f of x. Compare with the f of x, what's the change here? We substitute, see, we substitute instead of x, we substitute 4 for that. Okay, so now the rule says, see, in your rule it's 3x minus 1, 3 inputs minus 1, 3 times the inputs minus 1. But so now instead of the inputs, now I'm going to look for that inputs and then substitute that with 4. And that's why that's why I use parentheses here, and I highly recommend any of my students to use a parentheses anytime you throw in a substitution, a value substituted for a variable. Okay, so 3 times the inputs substituted by 4, formally x, generally x, but now 3 times 4 minus 1. Okay, and so now we come up with now this final value right here. So 3 times 4 is 12 minus 1, that's 11. Okay. And so now, so I need to make further notation. This is inputs, as you already knew. This is inputs, okay, as you already knew. But so now this one here is called outputs, okay, and this is output. It's an output, indicating it's something that came out from going through this rule or being determined by that rule. Okay, but the final value is not always the same. It's different values, and just like that, each one input gives you exactly one output. Okay, let's try another one. So now instead of f of x, I can put in f of negative 1. Okay. All right. We substituted the inputs, we substituted the variable primarily decided as the inputs for negative 1. So negative 1 substituting for x. So now in my expression 3, but instead of x, I write negative 1. So 3 times negative 1 minus 1. And now it gives me, so 3 times negative 1, order of operations, and then it gives me a negative 3 and minus 1, so it's a minus 4. So this is our outputs. Okay, this is again in inputs. Okay, and to step even another wild step for here, I want anyone to have a broader understanding of how important that is to have that symbol. So now allow me to erase this short little part right here, because it's just like any other one. But what about f of h? Okay, we don't always have to substitute a numerical value into your variable. You can substitute another letter into your variable, substitute another variable into your current input variable. So now what does it say? Your rule says, the rule for this function of yours says 3 times the input minus 1. 3 times the inputs minus 1. The inputs, how do we know this is the inputs? Because The input is the x variable. That's why you can say this rule here says 3 times the input minus 1. Get used to the fact that you read the rule. Read the rule. The rule says 3 times the input minus 1. How do I know this is the input? Because of that indicator. Okay? And so now, what's the consequence? The consequence now say f of h instead of f of x, f of h. That means the x, the input, is now substituted by h. So 3 times the input, but the input is now substituted by h. So 3 times h minus 1. So we consequently, and it's the way it is, and anyone arriving at this video lesson should be fluent enough with substituting an expression into another expression. Okay, so we consequently ended up with something, instead of a number, we ended up with another expression, 3h minus 1. Okay? And even further, we can go f of h plus 1, for example. F of h plus 1. This means this is now the entire h plus 1 is substituting for the x input variable. The rule says 3 times supposedly x minus 1, but now no longer x. We substituted x with h plus 1, so 3 times h plus 1, but the rule says 3 times, and that's why I put all that in parentheses, and now we're ready to multiply in. Distributive law, see, all of these are things that you need to know prior to entering this lesson right here. So 3 times h, 3 times 1 minus 1. So all together, distributive law says we have a 3h plus 3 minus 1, and all together we ending up with another expression in terms of h right here. 3h plus 2. Okay? So this is output, and this is also another final output based on the given inputs, h plus 1. Okay? So now that you know what a function notation is, and so still, I don't want to rush into the other problems that I brought up when I introduced about what a function is, and we will head it. We will head there, but I brought up for this function. So now, at least for the current time being right now, unless later on when I define otherwise, right now f is that rule. F of x is that rule 3 times x minus 1. Okay, so let's organize our work a little bit. So as far as the inputs, okay, and the inputs was the so as far as the input was regarded, or it was notated as the variable x, as the letter x in our expression here, and we used a few different inputs. We used -1, 1, and 4. Okay, and we even used h, and we even used h plus 1. Okay, the idea I'm about to show you, which is also a very convenient way, and I will formalize all this idea right here, but we can also put all of the results we have done, we can organize all of that into a table. Okay, so the outputs, now we can organize that into a table. So when x was given to be -1, then we calculated our expression to be -4. Okay, and then when it came to 1 right here, when it was f of 1, when input was 1, okay, then our final output was a +2. Okay, when the input was 4, we came to the output being 11. Okay, and when our input was a little bit abstract here, but h, then we came up with 3h plus 1, and I mean -1. Okay, and when it's h plus 1, we came down to 3h plus 2. Okay, so these are all the outputs. So now the idea now is that any of these different outputs, they switch values. They switch values, don't they? Okay, and now I don't want anyone to be too worried about these expressions, so let's erase out these expressions right here. Let's just focus on the part where we have the numerical values right here. So values, but in the end, all of these commonly share a meaning. These are the different various output values of this particular given function. So that's why very commonly you see a lot of people give the output another variable. It's a y variable. Okay, it's a y variable. Now, calling the inputs x and calling the outputs y is not always the case. You can call it differently like that, but this is just a tradition that x is used, meaning it's a lot of times of frequently enough that x is used to be regarded as the input variable, and then y is to represent the output value right there. Okay, it's a variable representing the output value of your function. Okay, so now in that way, what makes sense now is that we can see that the y as your output, any value of the outputs equals to, see, any value of the y variable, okay, equals to the output of the function. That's why this form right here, or specifically for this case, since our function is known to be a 3x minus 1, y equals 3x minus 1. Ladies and gentlemen, this is called the equation notation. Okay, quite commonly used as well. The equation, I shouldn't say equational, just equation function. I mean an equation notation. Okay, of the function f of x. Okay, it's just so you have seen the formal, the standard notation. Function's name, input indicator, and then the rule that helps us determine the output. And here, once we agree at this point, once we have seen the idea that the outputs can be a value, right? Then any of these outputs value can be regarded as a variable. So in that case, and whatever we named it, now we have here in this table here I named that y. So y equals y is a variable that equals the output value of this function. And then specifically in this case right here, it's y equals 3x minus 1 right here. Okay, and so for any of you who came out, who enroll into, who are learning this video after you have learned about linear equation, then that, yes, in this particular problem, that y equals 3x minus 1 is a linear equation. Okay, but now specifically in the concept of a function, then this is the equation notation of our function f of x, whereas this is the standard notation. Okay, this is standard notation. All right, so that should be enough for this particular problem. Let's get used to it, but now I can start picking up the pace a little bit. Okay, so we're still looking at and trying to get comfortable with using function notation. So that's among those problems that I brought up earlier. So let's look back at the vending machine problem. Okay. So there's a table. It was a table that decides the rule for getting a pop can or something like that, right? So we will have a soda can if at the price of $1. Okay, and then we will get a snack at the price of 75 cents. Okay, and we can get a water bottle. Okay, we get a water bottle at the price of 50 cents, and we get a coffee bottle, like a Starbucks bottle right here. Okay, so it's a coffee bottle, and at the price of $1.25. Okay, so that, and I call this a vending machine. So it was a machine, but now I also explained in the earlier part of this video lesson that it demonstrates the idea of a function. So the vending machine itself now is a function. This vending machine itself is a function. So money, this part right here is the input, okay, because you can give in and then it has a rule to determine what comes out. Okay, So the input here, let's give it a variable. It's in dollars, so let's use the variable d right here as for dollars. And the output here, what comes out from this function, from this rule, is a product from this vending machine right here. It could be a soda can, it could be a snack, it could be a water bottle, it could be a coffee bottle. So let's regard any of these as a product, okay? As a product, and it could be any of these products right here. And so let's call it a letter P right here, lowercase letter P. Okay, and so vending machine I can name. So now in the end, how do I use a function notation in this problem? Okay, I can name my function. How about VM? Doesn't have to be one single letter like f of x, right? Like g of x. Nope, doesn't have to. Okay, so my aim is to have my students who are learning with me to have a broader understanding. As long as you have a function's name, whatever name, letter's name, or whatever name you come up with. And then this function takes dollars. Okay, that's why in parentheses D, the amount for dollar right here, the money input. Okay, and then it comes out with the product. So it's a P right here. Okay, and so now the product as a variable P. It could be a soda can, that's a value. It could be a water bottle. It could be, P can be a snack. But in order to determine that, we have to determine that through this rule, VM of D. So now in that case, think about it. I can say, according to the way how we understand about the notation used here, the use of function notation, then in this way how I define my function, in this way how I notate my function, then VM of 1.00. This means $1 exactly. Okay, so VM of, well, and I should have said this is vending machine VM of D. That's how we say it. It's a function that VM is the vending machine right here, and it runs with inputs being the money in dollars. Okay, so VM of 1, that is equal to what? Soda can. So the only thing that's a little unusual for someone who is first time studying about this with me, but of course my main aim again is to have you have a broader understanding of what a function is. But you see, we don't clearly see a rule as an expression like the one I've seen earlier, that we have seen earlier, like a 3x minus 1. We don't have the rule written down, but here we have the rule expressed as a table. Okay, and take that idea, and I will eventually formalize and generalize all that. But here the rule says VM of 1 equals a soda can. That's how it works. Okay, and then what else do we have? VM function's name, VM of 0.5. This is the pricing that gets you a what? That gets you a water bottle. Okay, so now we have a water bottle. Okay, sorry for the shorthand writing because I'm running a little short at space right here. And then the vending machines, right? This function right here, we're inputting 0.75. That gives me a snack. Okay, it's a product, and that's why once again I'm reinforcing that the fact that P equals a VM of D right here. So this equal sign doesn't always mean, and it's time that you're gonna need to grow a little more mature in your understanding about the equal sign. It doesn't always mean equal as in a quantity equal a quantity. It could just mean a value inputted into a function, and it comes out with a value, and then that value right here is regarded as the P variable, the P letter like that. Okay, and so once again, this is the standard. This part right here, VM of D, this is the standard. The rule is here, but then this is the equation. Okay, the equation notation. All right, the equation notation of that symbol. Okay, and you see, just like the earlier little example I brought up, like I can put input and output on a table. This table itself already an input and output table right here. Okay, so just right here in this vending machine, the table you are currently seeing. Just that, we're putting that as a side-by-side table that organizes all of our results right here. Then see, any of these products right here can be regarded as the letter P as a variable, lowercase letter p. And then the input here was in dollars. So when dollar equals 1, inputting that into the function, the rule here says we're coming out with soda can. And that's the idea right there. Okay, so once again, it's P equals Vm of t. Okay, so admittedly, this example, this quick little example is a little challenge to digest, but if in case you're not so sure my intention, keep rewinding and view it. I have my intention so that you can understand the concept of function a little broader. Okay, but I promise eventually at some point we're gonna just go back and focus on all of those functions where it's just strictly math and expressions only. Okay, here I just want you to get comfortable and be ready to accept the fact that even if the rule is still there, everything about a function is still there. Okay, it's just we don't have that kind of rule where you explicitly see as an expression, as a mathematical expression, that's all. Okay, but the rule instead being written, being already expressed or represented here in this table already. All right, and so now we are ready for example 1 right here. To get anyone studying with me about function here to be real comfortable with how to operate with function notation. Okay. All right, so here we go. Let's call that example 1. And so in this example, I am going to give part A, part B, part C, but each part under this example is one separate problem on its own right here. So I would like to give as many as possible so that you can see the flexibility. You can gain some good flexibility, and you can see universally the property of that. Okay, a universal property of that. So here, part A, I'm going to start out with saying I'm going to be given. So now I'm departing. I'm using f of x again, but now I'm writing that as 5x minus 4. That means officially in this lesson we are done with f of x equals 3x minus 1. We're done with that. So now I'm taking that name. I'm taking that name to define another function, a different function. Okay, so now starting at this point on, f of x means a different expression. And there will be quite a few occasions out there, quite often in your mathematical life that you will see f of x again. So just every problem has a different definition for f of x. So here in this problem, your function is named f, no longer the other f. Okay, this is a new f. It's this rule right here. A variable x times 5 minus 1. Minus 4. 5x minus 4. And so now this indicator is indicating that this variable is the input. Okay, that means when we're giving a value to substitute for x, then we're going to have to substitute that into this x right here. Okay, so we have a function, there you go. We have a function evaluated, given right here, defined. That's another name, that's another way of saying our function f of x is defined to be 5x minus 1. Minus 4. So this is the rule. That's the function. So now the goal of this problem, I want you to evaluate, or let's evaluate together. Okay. So now see, all I need to write is f of 2, f of negative 1, f of 0. Okay. So now it's an indication. It's indicating that I want to come out with the outputs. So f of 2, here's how I'm doing it. The function's name is here. This name means that I have to use this rule. So 5 times the inputs, but now the input is substituted by 2, is given to be 2. All right, so 5 times 2 minus 4. Okay, and it gets me the output. It gets me the output 6. Okay, 5 times 2 is 10 minus 4, that's 6. So this is input. And this is how we use the input, and then now that's the output. Okay, and then the problem required us to also do f of negative 1. See, so this is an indication, and now once we see that indication, we know what to do with that. Negative 1. So the rule says 5 times the inputs. Now substituted by negative 1. So 5 times negative 1 minus 4. And that gives me negative 9. Okay, and then f of 0. See, and along with the way I'm saying it out loud so that you can start getting used to it. This is saying f of 2, f of negative 1, f of 0. Okay, and now this is going to be 5 times 0 minus 4. Okay, the output, negative 4. Okay, all right, and so now, again, just like in the earlier problem that I brought up, now it's a formal example. Let's organize this, and I will formalize all that idea. I will re-emphasize all that idea right here. But 2, negative 1, and 0, these are inputs. These are inputs, okay? And then 6, negative 9, negative 4 are the corresponding outputs, okay? So now we can organize them all in a table, okay? Negative 1, 0, 2. We didn't do things in this order, but at least I can decide to, you know, put the order of the input values in a certain order. So top down right here means from negative 0 to positive, and then negative 1 correspondingly gave me negative 9, 0 gave me negative 4, and 2 gave me positive 6. Okay, so now yes, this was inputs. Okay, and these are the outputs. We organize them into a table. Okay, but see, so the variable used here in this problem, that's the variable, the letter is used here is x to represent the inputs variable. Let's put it there. But for the output, like I said, it's just a letter's name right here. We don't always have to go with y. You can call this z. Okay, so the output here can be called z. Okay, so or y, maybe for anyone being a starter, let's just use y to get you comfortable, and then later on, as you are flexible enough, I can start using other letters' name. But be aware, this doesn't always have to be y for the output, and the same with x right here, the same with the input. It doesn't always have to be x for the input. Okay, so now in the way how I see, you can have y equals f of x. Okay, that's just nothing unusual, right? Or more specifically, this form right here, you can write it as, and this is not the main aim of the example, it's just the optional extra part that I want to put in to prep anyone for the next step right here. But this is y equals 5x minus 4. Okay, all right, so these are the value that we calculated. This is the end of our example, but additionally, I put in this component right here, and this part right here is the equation notation of our symbol, of our function. All right, so let's get comfortable again. All right, so now here we call that part B. Okay, so the wording structure remains exactly the same. We have a function given. So what is the next function for part B right here? How about I'm getting tired of using f for a function's name. How about let's use a little different letter, g. Okay, g of x. Okay, so there's a function, and this is indicating in whatever given expression that's about to come right here, x will be the input variable. Okay, so how about x squared minus 4x plus 1? Okay, so it's a different rule, and this rule here is regarded as a function with the name g. So g of x, as the rule says, square the input minus 4 times the input and plus 1. Okay, and then the goal of this problem, part B of example 2, let's evaluate g of 0, g of 1, and g of 3. Okay, and so now this indication is indicating that g of 0 means, now there's no reason to use f. Don't use the 5x minus 4 because that was f. This is g. Okay, so we have to take this rule that comes associated with that. So g of 0. So now this indication here is indicating that we're going to substitute 0 for our wherever it's known to be the input. So the input here appears in a few places according to this rule. So it's going to be 0 squared minus 4 times 0 plus 1. We substitute wherever you see the x with 0. Okay, and so now here the rest of the job here is just to do a final calculation. 0 squared is 0, 4 times 0 is 0. These two terms are 0. That's just 1. So this is output. Okay, we're done with one problem, one little problem. That's the end of this particular problem. And then g of 1, another requirement, another request of the problem here. Okay, so 1 squared, because the rule says we square 1 and then minus 4 times 1 plus 1. See, I really love that my student will understand a function is rule. So that's why I keep saying the rule says, the rule says. Okay, and so now 1 squared minus 4 times 1, the input, plus 1. Okay, that gives me minus 2. Okay, 1 squared minus 4 times 1 plus 1. And then g of 3. So now it's going to be the input square, that's the first term, minus 4 times the input. Okay, and then plus 1. All right, and so now it's negative 2 again. Okay, and so now here once again, one input comes out with one output. One input comes out with one output. Okay, one input comes out with one output. Someone may be worried about this one output has two inputs. That's okay for a function. Nowhere in the function definition says we cannot go that way, as long as inputting one value, giving out only one value. We're good with that. Okay, and so now that's the end of the example, but optionally I would like to organize all of these input and output in a table. In and out, input and output, that's the x. So this time, as anyone is viewing the video is starting to get a little better in terms of comfortability with the idea of using function notation. So let's now, instead of calling the output the y variable as the tradition's been using, then let's just call this is z. How's that? Okay, and so when x, the input variable, equals 0, we had an output 1 recorded here, and that was done through the calculation. That's why I said, the rule determines the output. Okay, when input was 1, okay, the output came out being negative 2. When input was 3, okay, the output came out being negative 2 again. Okay, so using a table, it's just a way, it's using the table here in this case, after we have done with the function, it's a way to represent the function. Okay, all right, and so let's try again to get comfortable. And by the way, so with this, since I assign all of the output values as a variable z, so you can say that in this function we can come up with an optional the equation notation right here. Z equals x squared minus 4x plus 1. Yes, it's our function, but instead of written in standard notation, this is equation notation. Okay, all right, so let's work with let's do more problem. And so now just back to what I said at the very beginning of this lesson right here, then in order to work with these problems, you are required to master all of your prerequisite skill in terms of understanding how to operate with a mathematical expressions and be ready for any kind of mathematical expressions at this point when you're learning this video lesson right here. Okay, so part C of the example. Let's say we're given a function, how about h of x, okay, and that equals square root of x. Anyone upon arriving at this video lesson is expected to understand what a square root symbol is, okay, and what it does for you. So here h of x equals the square root of x. It's our function. What does this function say? What does this rule say? This rule says for any input we give to x, for any input value that we give to x, we're going to take the square root of that input. Okay, so let's find out how it works. So now the problem wants you to see it's a way to communicate. I want you, as you follow this video lesson, to understand that my intention of this example is for you to get comfortable with how this problem is I'm communicating with you what to do with this problem. So now here's how I'm indicating it. H of 0. I want you to evaluate h of 0. Okay? And then h of 4. And then h of 1. Okay? So, and additionally and finally h of negative 1. Okay? So 4 little problems indicated here. So h of 0 as indicated. See, it's an indication. The rule says for whatever input that is, the rule says we take square root of that input's value. So now what's the output? Okay, so now it's clearly a mathematical operation. Can we take square root of a 0? Yes, we can. The answer is as an output 0. Okay, so now we have an output for that. It's a successful one. All right, so h of 4. Okay, h of 4. It means now we give this value for the input. We're giving in the value 4 for the input. The input is x in our problem. So now x is substituted by 4. So square root of 4. Simple enough. And hopefully in the later problems I won't have to verbalize it out as much any longer. Okay, so square root of 4, mathematically 2, or numerically 2. All right, the calculation, the understanding with your basic understanding of square roots, you know that the answer, the outcome here, the output here has to be 2. All right, and then h of 1. So h is this rule over here. The rule says we take the square root of every input given. Okay, so now square root of 1. Square root of 1 equals 1. So this is input, that is output. Okay, we're done with another problem. And you can see that I already pick up pace a lot faster compared to part A that I was doing it. Okay, so now how about h of negative 1? So that gives me a square root of negative 1. All right, so let's assume that right now we're only working with the real numbers. Let's assume that we're working only in the real numbers. Let's forget about complex number and any of that. That's not what the expectation of this lesson right here. So if we're only restricting ourselves, or if we're only working with the real numbers, then this value right here has an undefined value. We don't know what value that is. We don't know how to find the final outputs for a square root of negative 1 without learning the imaginary number or complex number. So here, in other words, we don't have a final output defined for this. Okay? It's just the way how our rule, it reached to a limitation. Okay? We don't know how to calculate square root of negative 1. If we ruled away imaginary number or complex number, if we're only staying in real numbers, then we don't know how to calculate square root of negative 1. So in that way, now I'm saying that this here, the answer is undefined. Okay, the answer is undefined, meaning we don't have a final output value for that, because this kind of operation, this kind of work right here, okay, does not take this input. It doesn't know what to do with that input, and we don't know what to do with that either. Okay, all right. So, and then just in that, yes, we can quickly. And I erased all that. That's the end of the problem, but I can quickly. Okay, so for input, we can quickly again organize all of those values: 0, 1, and 4. Okay, and then that gives me a 0 here, a 1, and a 2 here. See, input and output. Now, since the function already called the input variable, any of the input values, a variable x, okay, then here, how about the output? Here we can just call that, and I purposely try to stay away from y. I want you to break away from that that tradition of, y has to be the output and x has to be the input. Nope, it doesn't always have to be like that. So let's call this w, okay, lowercase w. Okay, no one's going to hurt us for that. No one's going to hurt me for that. Okay, so here the equation notation of this function, you can say w equals h of x. X is the input, W is the output. Okay, W is the output. And then so now, in the way how I'm seeing this, okay, so W equals square root of x. W equals square root of x. Okay, and then in that way, let's head out for the next problem. All right, so and I want you to be, to be exposed to as many problems as possible. So here we are given, how about a different function's name? A different function with a different name, q. This is my letter q right here, lowercase letter q. So q of x, okay, is to be 1 over x. Q of x to be 1 over x. All right, q of x equals 1 over x. So, and let's evaluate q of negative 3. Okay, and so q of negative 3. The math is straightforward here, and the rule is clearly to understand. The rule says for whatever inputs we're giving in this function, for whatever inputs, we're going to go 1 divided by the value of that input. Okay, so the rule says 1 divided by the input value. Okay, 1 divided by negative 3. And so now that with our understanding of this kind of operation, then it's going to be the final answer is negative 1/3. That's your output right there. Okay. The question also asks you to evaluate q of 2. We try a negative number, and now we try a positive number. Okay, that gives me 1 over, the rule says 1 over the input value, 1 over 2. Okay, and now that's just simply the 1/2 value. So numerically, or in decimals, this is about a negative 0.33 and a lot longer, and this is about a positive 0.5. Okay, but writing fraction as a decimal is not a requirement. At least in my class, I never require my students to be able to write these in fraction. As a matter of fact, I prefer that my students can leave the answers in fraction and get comfortable with fraction. Okay, and so now in the same rule over here, according to this rule of our function q, and see, at least in example 1, part D of this video lecture, I named this rule the function q, but other problem, again, somebody else can use this name for a different function. So be ready for the letter that we name our function as well. A function's name can be whatever. Okay, we have seen f of x, we have seen g of x, we have seen h of x, we have seen q of x, all over. Okay, and so now same rule right here, same function. Okay, 1 over x, 1 over the input. The question in this example is asking us to do q of, how about q of 0? Just write it down. Just write it down. You don't need to worry anything too far ahead. Okay, just write it down, q of 0. And what it means, just like how I have done that earlier, what it means is 1 divided by the input being now 0. Okay, and then now let's proceed according to the rule. According to the rule, 1 divided by 0. Oops. We don't know how to divide by 0. Okay? And now maybe this is the first time that you hear my own joke, but as long as we are human on earth, we will never know how to divide by 0. Mathematicians for generations have tried, but unsuccessful. We've never come up with a way to divide by 0. It's just a mystery on earth. Okay, so now I have to say undefined. We don't have a value for that. Just similar to the earlier situation where square root of negative 1, okay, or in general square root of a negative number, we don't have a value defined. We cannot proceed with the calculation, so we call that, we have an undefined value. So the rule is just the rule. And now that I start leading you into that way, and we will get there in some other lesson right there, but there's in the way how your function is, in the way how your rule is, some input is impossible. Some input is impossible to be substituted, to be given into a function. And we will get to that idea more specifically later on. Okay, but for now, just for this rule, according to this rule, the way how it was written, the way how it was defined right here, then it cannot take this input. So input 0 is undefined. Okay, we don't know what the output is. All right. So again, in that way, we're done with part D, surprisingly. And again, let's give that a letter. I mean, let's organize all of the values in a table again. So input, output, and now do we always have to put the input on the left column and output on the right column? Nope, doesn't even have to. You can put input here and output there. You can even put your table in a side way where input and where's output right here. The point is you're understanding what you are doing. Okay, and so now I have done -3 and 2, okay, and 0. Okay, and we had undefined here. Okay, we had undefined. This is a negative 1/3 as the output, and this is positive 1/2 as the output. Okay, and so the function already in the problem already named this variable for the input x. So now we can name this. Okay, you can call that whatever letters. I'm running out of creativity on my own. How about let's just call that s. Okay, let's just call that s. So here I'm seeing that s equals to, in this problem at least, s equals q of x. But then specifically s equals 1 over x. Okay, this is the equation. The equation notation. This is not the part of the example, but I just decided to go a little extra. Okay, a little bit of an extra mile right there. All right. And last one in this example. All right, so part E of the example. Again, very similar wording. How about let's call that E of t. Okay, E of t equals 2 to the t. There's a different rule. Okay, so now this time this is the first one among the many problems I've done. Everything so far I've been using, the problem has been indicating x as the input. But see, now I really want you to understand x is not always the name of the input, the name of the input variable. You can call it t here. Okay, so now the function's name is e. Okay, e, and it takes, in this expression, anywhere you see the t variable, that's your input. So now the problem is asking you to do e of 0. Okay, e of 0. E of 0. That's the way how we're saying it, but it means 2. The rule says we raise, this is now the input variable, so we raise 2 to the input variable. So 2 to the 0, okay, the input value right here. So 2 to the 0 is 1 algebraically. And so it's a requirement that you know how to operate with 2 to the 0 right there. Okay. The problem also asked e of 3. Saying it out loud, reading this notation out loud, e of 3. But how do we do that? How do we work with that? 2. Okay. I substitute 3 for the t. And so now how it works, 2 to the 3rd power, 2 to the 3rd power. And 2 to the 3rd power is 2 times 2 times 2. 8. That's the output. Okay. And then, so now e of 1. Okay. That's how I'm saying it out loud. But that means 2 raised to the 1st power. Okay. And that's now just 2. And the last one here, e of negative 1. Of negative 1. And it means it is 2 to the negative 1. This is, so 2 to the negative 1 algebraically 1 over 2 to the 1st power, which is a 1/2. Okay, and another one, another extra one right here in this problem, e of -2. E of -2, it equals 2 to the negative 2. Okay, and 2 to the negative 2 algebraically equals 1 over 2 square. Okay. And then if anyone is having a question about how this 2 to negative 2 equals 1 over 2 square, you need to see me either find a way to contact me with my school email address, or find a way, some other way to communicate with me outside of the lesson here, so I can explain right here. But this is going to be a 1/4. Okay. All right. And so again, we have inputs and outputs easily calculated, and let's put all of these values in a table. So now I can go sideways because I know it's going to be a little lengthy right here. So input, okay, does it always have to be on the top row? No. And then this time, see, all of the values for the input variable can be regarded as a variable t. So input is a t variable. I went with and let's organize these. -2, -1, 0, 1, and 3. All right. And then I came to, so the outputs were those, okay, this was a 1/4 here, this is a 1/2 here, this is a 1 here, this is a 2, and this is an 8. For those corresponding outputs, and you can always check back with by rewinding this video lesson right here and check back with these the output values right here. But see, so with these output values, we can regard to that as a function, as a variable y right here. Okay, so this is y equals 2 to the t. Okay, that's in equation notation of that. Okay. All right, and so now we are ready for heading into example 2, just to further enhance your understanding about how convenient it is to use a function notation, the function notation that I introduced just earlier. So let's now look at example 2. All right, and so let me spend some time writing down the wording description of the example. So now I'm going to say let f of x. So now we define our function, the same function f of x, and of course I'm just like any other professor who just can escape from that tradition that's most of the time using f of x to be our function name like that. But so just want you to be aware that you can use a different name, function's name. It's just me that I'm a lot of times stuck with that tradition right there to use f of x. But anyway, so it's different f of x compared with the earlier one in example 2, example 1, and also it's the different f of x compared to the very early example I brought up. Okay, so here we're gonna have to redefine our f of x. We have to give it a different meaning. Okay, so now and this wording description is about to describe our new definition of this function f of x right here. So let f of x be given as the following table. As the following table. Okay, so here's the table, and I'm going to list down a few values. So now I'm going to, in this table, we're going to have a row having a list of values for x. So let's say we're looking at 1, 2, 3, 4, and 5. Okay. Okay. And so now, at least up to this point, you have already understood that this is the function f of x. And with at least in this indication, once you already know that our function has the name f, then the x here is the input. So that means now, at least before I complete my table, you can start looking ahead at this table, and you can see that these are the different values that our variable here can take. And this variable here, relative to this function, this variable is the input of that function. Okay, where any of these values for the input is responsible for determining different outputs to that function. Okay, so that's the goal right there. So now here's what the table says. And the table is the way how this function is. So f of x, the output of f of x is going to be, so now for the f of x row, I have 8 corresponding to 1, 6 corresponding to 2, 7 corresponding to 3, and 6 again, and 8 corresponding to 5, and another 6 here corresponding to 4. Okay, so that's the table. All right, so now, after I completed the table and before I finish writing down the exact the request of the problem, the final instruction of the problem telling us what to do with this function, then let's try to understand what that function is. So you see, these are the different inputs, and these are the different values of the x variable. But then according to the way how we read and understand about after we have our understanding on the function notation, then the x here is playing in the role of the input. Okay, and so now, so just in that way, this function, this table lists down a few different values for our input variable. Okay, and so now we are about to understand what these corresponding values for this f of x row over here. Okay, so now we want to evaluate. Okay, so f of 3. Okay, so this says out loud, this reads out loud f of 3. But it now means, so I want you to be in a completely different situation compared to the earlier example. In example 1, things are easy. We saw the rule clearly as an expression, as a formula. Any of those problems we were doing back in example 1, we saw the rule clearly. Okay, we have seen a rule written down specifically. Here the rule is right here. It's right through this table. It's a surprise, it's maybe a shock to anyone in the first time, but it's time that we start getting used to it. Okay, so here's the rule. The rule may not be explicitly written as a formula as you have seen in example 1, but here's the rule is telling us that, hey, when input equals 3, when the input variable equals 3, this is the output. That's what the meaning of this table is. Okay, so this table is not only representing the function, but it also defines the rule of our function. So I don't need anybody viewing this video to worry about representing the function, but right now this table defines the rule of our function. So the rule says, and is that a 2x minus 1, is that an x squared? That's not the matter. The matter is right here. The rule of this table, just like what I brought up earlier in the vending machine, the rule says when it's a $1, you come out with a soda can. When it's a $1.25, you come out with a coffee bottle. So here the rule of this table, the rule of this function is given right here, is expressed right here in this table. The rule says when your input is a 3, you're outputting. Okay, you come out with an output being 7. Okay, so right there, that's how we're reading it. All right, and so now once we're clear with the idea of how we read output's value right out from a table, and now you are starting to get comfortable, you're starting to be acquainted to the idea of having a function, the rule being given as a table. And it's quite limited, but that's all here. Okay, so now, aside from that particular little evaluation problem, what about f of 5? Okay, so f of 5, input is 5. The input is 5. So now we're going to look it up on this chart right here. When input is 5, where's the output? Right here. And that's why we had that label at the heading of this bottom row over here. The label is f of x, is indicating that the outputs, that's what it's for, the output. Correspondingly, when the input is 5, the output has to be 8. Okay, input, when it comes out to 5, output is 8. Okay, that's how it meets with that entry right here. Okay, and so now output is 8. We found the answer right out from the table. Okay, and so in that way, well, what about f of 2? The way we're saying it out loud, f of 2. Output value, input now is 2. So on the input row, we search out to x equals 2. And then when x equals 2, correspondingly, this table tells us that the outputs, the value of the function has to be 6. All right, so that's the output. Okay, so how about another one? F of 0 equals, okay, so in this case right here, what do I have? F of 0 equals, do we have a 0 here among the inputs? Among the input values being listed in this table, we don't have one. We don't have one listed for x equals 0. So consequently, we don't have one. We don't have a value corresponding for x equals 0. So in this case right here, we have seen that term earlier. This is where, again, I'm saying f of 0, the answer to that is an undefined. Okay. Having a little bit of a narrow space. How about I'll write it on the other side of this other part of the board here. F of 0 equals, well, it's an equal, but really the answer to that is an undefined. All right. So now we have seen and investigated a few cases. And the idea, and my whole intention, my entire intention of this problem is to introduce, to get anyone learning from this lesson, to get anyone learning from this lesson acquainted to the idea that a function can not only be given as an explicit formula, as you have seen earlier in example 1, but a function can also be given quite commonly as a limited table like this. And any input values that's not listed in the table, we can just simply say that the answer is undefined, because there was no rule for that input. There's no rule for that, what's coming out of that input. And that's what undefined means. Okay, and so these are the answer, and at this point, that's the end of our example, but allow me to do the similar thing compared to the table, compared to example 1 right here. So that similar thing that I'm about to do here is, it's just an optional thing, but it will start building your foundation right here. But so, yes, it makes sense that the x variable here is the input. Okay, clear enough. But now, these different output values right here, we can regard to that as the y variable. Okay, so I can say y equals f of x. Okay, y equals f of x. I'm a little short of space, so I'm writing that in a little bit of an awkward way right there. Okay, but any of these values, okay, we have two values for 8 right here, and we got 2, 6, and we got 7, a 7 here, but any of either an 8 or a 6 or a 7, these are all different values of our variable y, but the variable y here is the output. Okay, now we got that clear, and this is the input. All right. And so in this way, now I need to erase the work we have already done. And so in this way, once again, just like we have seen earlier in the earlier examples, that here we can freely say that, so in this way, y equals the rule of the function f of x. Okay, it's just sadly for this problem, we won't be able to proceed to write down any more explicit than this, simply because the rule was given as a table instead of a formula, instead of a mathematical expression. Okay, and so here it's just the equation notation for that, but this is about all we can write right there. So y as a variable for the output equals to whatever comes out as the output based on any given x expression. So y equals f of x. Okay, all right, so now that's the end of our example. And then this, needless to say, the table itself defines the function and also represents the function. So you can also, another way of saying, you can rewrite the table as following: input, output, right? Similar to what I've done earlier. So the x here and the y there, right? And so we got 1, 2, 3, 4, and 5, okay? And I have 8, 6, 7, 6, 8. This is that same exact table earlier, but now I'm writing that as a table of values that's very similar to those that you have seen back in example 1, throughout example 1. All right, so that's everything about example 2 right there. All right, and so now, since we're still wrapping up with that idea about being able to work with the function notation right here, then there are a few other details that I would like to emphasize on. Okay, and so let's look back at example 1, and I'm going to pick maybe 1 or 2 problems from example 1 right here. So I'm going to say back to example 1, okay? And let's say, you know, how about just out of just a random selection right here, I'm going to pick part B right here. So we had our function there given to be, so that was the one we worked with. Part B was, it was a g of x, okay? And the function was x squared minus 4x plus 1. X squared minus 4x plus 1, and we came down to a table of values. So in the problem itself, I clearly indicate which variable was the input and which variable was the output. We got it all clear at the end of that example 1 part B already. And then I still remember clearly I called this, this was z equals x squared minus 4x plus 1. That was in equation notation right there. And so as far as the table of values, see, the x now and the z has one column. It doesn't always have to be the input on the left-hand side and output on the right-hand side. It doesn't always have to be like that. Okay? But so here's the thing. I want to emphasize a few other things before we move on earlier. See, for this problem in part B, the problem asked us to do x of 0, x equals, g of 0, or x equals 0, x equals 1, x equals 3. Okay? And then we came out with final output value, and that was a 1 here, and that was a minus 2 here, and that was another minus 2 for these for the z column. So that was the table of values we've seen back at the problem itself right there. Okay, so nothing surprised about this. Nothing surprised about this. But so here's the thing. Just simply looking at this, now I want to enforce another term right here that you might have seen here and there already, but it's now time to formalize it. You see, in this table of values, right, when we're looking at that, and we were clear with the fact that the x here was the input. And so now think of how we have been doing it. So there's no rule that we have to choose the inputs in such a way, that way. So in other words, there's no restriction about picking a value for input. The problem suggested these values 0, 1, or 3. Once the rule was given, the problem suggested for us that 0, 1, and 3. But I could have also made another table. I could have also chosen for myself the input x and the output z to be, you see, I could have also chosen completely disregarding these 0, 1, and 3. 4, -1, and -3. I can select these values completely randomly, okay, and independent with whatever suggested from the problem itself, okay. I might have said the textbook, but that's really just my own problem that I prepare right here. But see, here's the thing. So that's the reason why input variable is very commonly regarded as the independent, because we can choose it independently, the independent variable. Because think about how it was done right here. We can independently, I can choose 0, 1, and 3. Okay? Anybody else can choose these values and even more values. You can, to keep the problem short, we went with 3 values to try for substituting in x, but we can keep going further. We can keep throwing in more values. And then no one is telling us that we have to choose 0, 1, or 3. That's what I meant earlier by there's no rule about what values to choose for the x. There's no rule about what to choose for the x. Okay? And that's why it's independent. But now for the y value, now with this function we have a specific rule over here. So the z, now I set the y value. See, once again it shows clearly that I'm still stuck with that tradition, but here I chose z as the output. Okay? So the tradition is a lot of times y is the output, but it's not always. I want students who study with me to be, stepping away from that tradition right there. But z here is the output. So the output is a lot of time very commonly regarded as the dependence, okay, the dependence variable. And now it's a good time to learn about these, because see, a lot of times when you are writing your function in you're writing your function in an equation notation like this, then between the two the variables being present here, then the x here is playing in the role of the independence variable, and the z variable, it's another variable. This is a variable, the other one is a variable, but this variable z here has value depending on what we gave out first in line for x. Okay, that's why the output variable is regarded as the dependent variable, okay. And so just like that, so that's how it happened throughout the entire example 1 right there, the entire example 1. Okay, so just now allow me to switch to the other board space right there. Okay, so just now on that example 2, and now you kind of see, you're seeing where I'm heading to. So back to example 2, I'm reintroducing that idea right there. Okay, so our function, in the end, the table of values we've had was x and then y right here. Okay, 1, 2, 3, 4, 5. Okay, but see, this y was agreed to be, these values 6, 7, 6, 8 right there. Okay, and then we saw at the end of the example 2 that we can write. So this table was the rule for, we take any inputs here, we choose any inputs randomly on that given table initially, and then we come out with that value dependently. And so in that way, once again, we came to that conclusion that y, the value for this variable y, because we assign the y variable to these output values right here. So the y variable, okay, is the dependence. The dependence variable, okay, and the x right here, see, the table was given, but you see, we can start out doing x equals 5 first, or we can start out being x equals 1 first, and then hit out to x equals 0, which was an undefined case right here. But see, in the end, the inputs there was the independence variable. All right, so now you are familiar with all of those terms that are being used out there throughout math professors and other people doing math and mathematicians. Okay, and so now some more understanding. So now as I'm introducing that idea about, in an equation setting like this, then one variable must be the independent variable, and the other one has to be the dependence variable. Then think about, in that setting, then it's, again, if we're looking a little further into this equation notation of any of your function right here, then the dependent variable always stands by itself, coefficient 1, no special power, just but one standalone single variable by itself, like a 1z, 1y, that's it, not even a negative, just z equal. Okay, and then on the other side, it's an expression, it's a rule, that's apply on the input variable. Okay, and so now in that way, another way of saying, this is a way to say in words right here, but see, z is a dependence variable and x is the independent variable, and then z equals to the outputs of a function of x. And so in that way, another way of, you will hear people say a lot of times is, in this particular equation, I'm saying that the z variable, I'm talking about now the role of these two variables, how they are related to each other. Okay, then z being z as the function. Okay, this equation this equation expresses z as a function of x. Okay, see, this equation expresses z as a function of x because z is the dependent variable and x is the independent variable. Or another way of saying, just even shorter than that, right from this equation you can see that z is a function of x. Okay, that's another way of saying it. Okay, and so now back in example 2 where I had it on the other board right here, then you can see that here this equation says okay, that equation expresses y as a function of x. Okay, or another way of saying, right from this equation, you can say that y is a function of x. These are equivalent wording. That means the same thing. Okay, it all comes out from the way how we understand about the equation notation of a function right there, of a function. Okay, so to get viewers and students of mine more comfortable, so let's look back at example 1 and let's pick out randomly some other problems that we did in example 1 to get you comfortable with the way of how we saw it. Okay, and so here let's look at example 1, but I'm going to randomly pick part E. Okay, part E. So back at example 1, that was only an optional step, but I used that optional result I pointed out there to dig in with further details like that. So the final equation notation of that function there was a y equals 2t. Okay, and we did this. We arranged things in a table of values, and so the problem there in example part E suggested for us that t equals and we had quite a few different t values right here. Let's see, if I look back carefully, it was -2, -1, okay, and then 0, 1, and 3. Okay, and then we had these, so these were now needless to say this is the independence variable because we can choose these, the problem chose these for us, suggested these values for us, but we can choose, we could have chosen different values like that, so these are chosen independently. Okay, no rules, no restriction about how to choose or what to choose with these values right here for the input. Okay, but now for the output, and we call the output as we regarded all the output value as the values as the y variable back in that problem. And that's why we had that this equation y equals 2 to the t right here. But in the end, see, being the dependent variable here, then we came to a positive 1/4, a positive 1/2 as the outputs. Okay, and these are all values, but they are dependent on the corresponding the input right here. And then this was 1, this was 2, and this was 8. Okay, and so now clearly, now looking back at that particular example 1 part E, and now with our extra understanding, but now quite important to know that information, then once we see this function here in equation notation, then clearly I can see that y right here as okay, this equation expresses, okay, y as a function of the t variable. Okay, or even in short, I don't even need to rename that function. I don't even need to say it out. I can just say right from that function, I see that y as a variable is a function of t. Okay, because see, we obviously had this y equals e of t. It's a function of t. That's what it is. okay, or y as a function of t. All right, so that's some further details that I would like my students to have like that. Okay. All right, and so the last piece of information before we end this particular video lesson right here. Now, there are still a lot more details that I haven't mentioned in this particular video lesson about functions, and that will wait into a different video lesson right there. But right here in this video lesson right here, let me wrap it up with the idea of how we can how we can use table to represent, okay? Or it's not even about how to use it. I mean, the idea, you have seen it all over. It's just now time to generalize it. Okay, so how about as a subtopic, I would say table, okay, as a representation, okay, of a function, or using a table as a representation of a function. It's just all about the idea to organize our function, to make it clear for whoever worked with the problem to see where the input is and where the output is. Okay, so let me dive right back at that example 1 again. Okay, and that example 1, back in example 1 right here, part A, our function was f of x equals 5x minus 4. Okay, and we came to the following, we see the function itself already gave us, that was the case, right? The function itself gave us x right here being the input, so we couldn't change that. Okay, but the outputs here, we had our choice to name the output, so I named it throughout our work. It was the y variable. Okay, and so we came up with that final, with that optional equation notation, y equals 5x minus 4. Okay, but in the end, now input and outputs we put as a list at the end of the problem right there. That's as a list where I organized out. So this is in earlier algebra courses, those algebra courses you've learned prior to this class right here, we call a table like this the table values. Okay, and that idea about using the table values lives right here again when you're working with function. So now, table of values, how does that help in a problem like this? We list down for the column that's corresponding to the x inputs right here. Then those values we did was -1, 0, and 2, and the outputs correspondingly were, see, that was -9, -4, and 6. Those were the ones. And these were only the one being suggested, being asked by the problem, but we could have also done same problem, but we could have had other values. Remember now, I have explained it earlier. The x values are chosen independently. So outside of these values that the problem chose for us randomly, we can also do -2, okay, and then +1, okay, and 3. And -3, okay? And usually it's also a good practice to organize all of these independent variable values in increasing order or decreasing order, depending on how you want it, okay? But here I just want to mainly focus to emphasize on the idea that we can use a table. So once we've had all of the input and once we've had all of the output values calculated, then it's a good idea to organize and to put all of those values, those corresponding pairs. See, inputs, that input -1 paired up with -9, that input 0 paired up with -4. Now, I did not do this back at example 1, but see, -2 times 5, that is a -10, minus 4 is a -14, for example. Okay, so we have another pair of values, x and y, input and output, another pair of value. Now I didn't get one ready for this, so 5 times 1 is a 5 minus 4. Okay, it's a 1. Okay, and then that is an 8. Okay, and then actually I was thinking of the other rule right there, but that's an 11. Okay, and then this is a minus 19 right there. So this is the idea. We use a table that represents that puts two columns. One column is listing out all of the inputs, the other column listing out all of the outputs. And once we can put it in the table, it's also a good idea that we can, I didn't do that here yet, but it's also a good idea that we can just sort out these inputs values in certain order right there to keep things organized, so that later on when we get into graphing and putting these into a plot, it becomes so useful for us. Okay, so this is the idea about we using a table, right, as a way to represent a function. Okay, it's just we simply making a list. Simplest way of putting it, we're making a list of input and output correspondingly. Okay, so this is in this way in any of the problems of example 1, then table representation is sort of like the last step after you have seen the function and have done a whole bunch of calculations. Okay, but then think about that example 2 I still have on the board here. Then the table itself initially was also the rule of the problem, and so having a table representation is so important at this point, because a lot of time it's not only just a representation of the values here, but it was initially given as the rule. Hey, input here, this input's 1. Anytime the function takes inputs 1, it gives you output 8. Anytime the function takes inputs 2, it gives the output 6 right here. And so it was the table that defines the rule, that call the rule of the function. But then once we are done, then that table itself was that way to represent the function values, like the inputs, outputs correspondingly. And then it gives us a sense about organizing the values in a certain order. Okay,